Hi, this is Graham Helfrich, Technical Advisor Manager for the Engineering Software here at IHS Markit. Welcome to the weekly Did You Know episode, where we learn how to do something of value that you probably didn't know about your IHS Markit engineering software. The human body has amazing senses. It's not really the sensitivity, but it's how well calibrated we are to sense things that are out of normal. Now let's imagine that we're a woodworker and we're very experienced and we've calibrated our senses for woodworking. Well, we're going to be using our hearing to hear the load on the machine we're using and the sound that we're having on the wood. We're going to be using our eyes to see what effect we're having and adjust what we're doing based on what we see. We're going to use our smell potentially if we're burning the wood or if we're loading the machine up too hard, maybe burning a belt. And we're definitely going to be using our touch and even temperature to understand how much pressure we're putting while we're woodworking. Okay, so we use all of these senses in combination, but it's the fact that we're calibrated once we've practiced something to use them better. So we know these senses in the human body are amazing, but imagine if we could sense when there's something wrong with our pipeline, like a liquid slug or some other kind of blockage. And that's what we're going to talk about today. We're going to talk about calibrating your pipeline model to find liquid slugs and increase production. Now, to give you an idea what I'm talking about, let's imagine that we have a pipeline and there's a million cubic feet a day flowing through it. We know the pipe diameter and length. And we have a known measurement on one side of the pipe, 100 psi. This might even be a compressor inlet pressure. So we can use a equation or a pressure loss correlation to calculate what should the pressure loss be in the pipe and what should the pressure be on this side of the pipe. In this case, 110 pounds, saying that we're losing 10 psi along this pipe. Okay, but what if we go ahead and take a measurement over here on this side of the pipe and we measure 130 psi? Well, that's different than 110 psi. So there's a disagreement between the pressure loss occurring in the pipe between the correlation and the measurement. I'm always going to trust a measurement. And this is just a factory reality. Do pipeline models always represent reality? Not always. And it's part of our job to question where the model doesn't match field measurements and figure out why. Now, a lot of the time, the reason for this is that there's something going on in the field that we just don't know about, such as a partially closed valve, some construction equipment left in the pipe, and a lot of the time, a liquid slug that's built up and is causing this disagreement. So let's talk about how to calibrate a gathering system, whether you have 10 wells or 1,000 wells, to find these issues in the field. So here I'm in the IHS Markit Piper software, a gathering system software, which is basically a really nice and easy to use pressure calculator. I've got my wells over here. I've got my pipelines in green and also in blue. I've got my delivery point and my compressor here. And what I want to do is I want to calibrate this. I want to see if I can get a model that matches reality. Okay, so I'm going to go ahead and import our measured rates and flowing pressures from each well. Okay, so I got my well name, my measured gas rate from each well, my measured line pressure at each well. Okay, so I've got my gas volume, I've got my pipeline length and diameter, and I've got a known delivery pressure, which is 450 pounds at my compressor inlet. So I'm going to use that information to back calculate what should the pressure be at each wellhead based on a correlation. We'll go ahead and calculate. Now what we're going to look at now are the results. Okay, so this particular well right here is producing 1,000,000 cubic feet per day. And the software's telling me we should have 458 pounds of pressure at this well. Okay, that's what the computer's saying. The measurement that we took in the field is a little bit higher, 465 pounds. So there's a delta P of about 7 pounds between the model and the reality. Okay, that's pretty good. That's pretty close. But as we can look around, we can see that some of these, here's a 4-pound difference, pretty good, 7-pound difference. But you know, once you get to hundreds or thousands of wells, you can't afford to spend time manually looking at this delta P for the calibration. So instead, we're going to use some colors to make this a lot easier. So we've got the pressure calibration map. What this is doing is it's taking that delta P value and it's just making it a color. So blue is basically a good match, and red is telling us that there's something wrong. There's some difference between the model and the measured pressure in the field. So for these wells over here, we can see that for this particular well, we're predicting only 600 pounds, but we're measuring 650 pounds at the actual well. So for some reason, there's an extra 50 pounds of wellhead pressure at this well that can't be explained through normal pressure loss calculations, okay? And the same is for these wells here, okay? Now, one thing I see happen a lot is the solution to this that some people think is to go ahead and change the friction coefficient or the roughness of the pipe. And all they're trying to do is match the model, but they're not actually getting down to the root cause. Why is the model wrong? Okay, the problem with that is A, we're not learning anything about what's happening in the field, and secondly, once we change the volume through these pipes, now it's going to have the wrong pressure loss calculation and the wrong pressure drop. So really, doing this calibration is an opportunity to find out something wrong in the field that we didn't know about, like a partially closed valve, a liquid slug, etc. Okay, so putting our detective hats on, how do we rule out whether liquid slugs are even possible in this area? Well, it all has to do with the velocity of the gas. Okay, so if we look at a pipe, we've got gas going through here, and usually there's water too. Now, in this case, we have some liquids trapped in the bottom of this pipe, and you can imagine the pressure loss that's going to cause. Why does this happen? Well, we need gas to be moving and pushing the liquids along through the pipe, and there needs to be enough gas velocity to do that. Once the gas velocity gets too low, these liquids start to build up and cause problems. This happens a lot when people are oversizing pipes. If you're pigging all the time, you know that it's probably because the pipe is too big. So how do we actually know what velocity we need? Well, we've written a few papers on the subject. One of them is about estimating what that pressure loss is with a liquid slug in place, and the other is how do you calibrate your pipelines to address this issue. As a result of these studies, we've come up with this predictive method. So what is the minimum gas velocity based on your pipeline operating pressure? Okay, so basically if our gas velocity is above this black line, we should be safe. We should be able to move all the liquids through the pipeline with that gas velocity. But once we get our velocity a little bit lower and definitely in the red area, now we're at risk for liquid slugs to occur in the pipe. We can actually apply these calculations directly in Piper to see where this could be occurring. Okay, so blue is good. That means we have enough velocity to be moving liquids along. Red is bad. It means that there's the potential for liquids to be trapped. Okay, what we're doing here is we're putting our detective hat on and trying to narrow down where do we need to go to the field to take some measurements to isolate the problem. And that's exactly what we did. We saw that this is where the calibration is wrong. We saw that red pipes indicate the potential for liquid slugs, and combining this with the topographical map, we can assign our field engineers to go take some measurements. So the results came back and there was an extra 50-pound pressure loss along this pipe segment and this pipe segment that we didn't know about once we took some measurements. So we're going to go ahead and account for that in the model now that we have learned that. Okay, so I'm putting these pressure losses in here to measure the liquid slugs that we went and measured. And there was a 50-pound pressure drop at each location that was measured in the field. Okay, so as a result, we can go ahead and recalibrate and recalculate our system and see now everything is blue, which means we've improved our model to represent reality, and now the prediction of the model is matching the measurement in the field. Okay, we're within a couple pounds of reality here. Now, if you don't already know, the reason this calibration is so important is anytime you want to do future forecasting or what ifs, tying in new wells, connecting an RTA model, IPR models, you need to have this solid calibration completed as a base model just to get going. Otherwise, things can be unreliable moving forward. So the results of this particular study is that it was decided to pig those two lines, and that flushed out about 1,000 barrels of condensate, which was worth about $52,000. And the benefit of dropping the line pressure by pigging those lines was increasing the total rate in the system by about 1 million cubic feet per day. Now, if you're worried, Graham, that system was kind of small, I have thousands of wells, don't worry. This is This is a gathering system that has over 5,000 wells that was used with Piper to solve these kinds of problems and many more to develop infill drilling plans. So what does this mean for you today? Well, if you're worried about low velocities in your pipes, whether it's now or later, Piper really forces you to ask the right questions, like I've shown you today. Next, these are really free opportunities, and they're ideal whether you have an old gathering system or even a newer gathering system, but you think the pipelines are too big. The other nice thing about this is it doesn't require any reservoir information or wellbore information. This calibration can be performed at the start. It can also be done as a regular check, kind of as a monitoring technique. And finally, we have IHS Piper engineers who can help you and provide their experience to help you get up and running and your system calibrated as well. Now, as far as calibrating our senses, it's taking you your entire life to calibrate your senses to what they are today. The good news is you don't have to wait that long to calibrate your gathering system using Piper. And that's it. I want to thank you for your time. If you have any questions, just call me or email me and subscribe to be notified of next week's episode.